So last time in the previous previous lecture, what we saw was that we saw a new formulation which we were calling the Neyman-Pearson formulation, where our goal was to find a test which minimized the probability of error of type 2, while the probability of error of type 1, the misdetection, the false alarm probability, is kept below some nominal epsilon. And what we saw was, so we call this minimum probability of error of type 2 the minimum probability of error of misdetection. Uh, we denoted this by this beta epsilon W0, W1. And we saw a very simple calculation, very simple but actually quite useful and very powerful, which shows that if you have a threshold tau, which is a large probability upper bound on the log likelihood ratio of W0 by W1 and large probability under W0, then a threshold test with this threshold has probability of error of type 2 less than 2 to the power minus tau. In particular, for the case where these distributions were IID, what we saw was that tau can the probability of error of type 2 can be made to go to 0 very fast, as fast as roughly 2 to the power minus n times a quantity which was some expected value of log likelihood ratio. So it can be made to go to 0 exponentially fast, okay, exponentially in n, and the exponent had a very simple formula. So this exponent which we discovered last time is called the Kullback-Leibler divergence. It is an alternative notion of distance between distributions, which will complement our definition of total variation distance. And this phenomenon that the probability of error can go to 0 exponentially rapidly is related to a very popular result called Stein's lemma. So today in this lecture, what I'll do is I'll discuss this Kullback-Leibler divergence and I'll present Stein's lemma. So Stein's lemma is a very important result for hypothesis testing as well as information theory. Okay. So yeah, so this is the quantity we saw last time. We saw that expected value of p of log. So here, by the way, some small confusion about this notation. I often switch to small p and small q. Basically, these are my proxy for densities, which is just PMF in this case. So no difference between PQ and P. There's not much difference. And P is the distribution. So I switch to small when I'm thinking of densities, but I will not be consistent with this notation. So please remain active and fix this notation in your head all the time. Okay. So the quantity EP, this guy here, the expected value of log likelihood ratio under P, is called the Kullback-Leibler divergence, DPQ. Okay, I'll denote this by DPQ. So just like small dpq, which was total variation distance, this is the second distance that we will look at. We will just call it divergence for short, but it was used in statistics by Kullback and Leibler, and it's called Kullback-Leibler divergence, KL divergence for short. And I'm not using a comma here, I'm using this part, this function here, a pipe here, mainly because a double pipe here, because it's not symmetric in P and Q. You can check that this definition is not symmetric in P and Q. If you expand this expected value, this will the total variation, the Kullback-Leibler divergence will look like this. It's summation over y, py, log of py by qy. And it is the counterpart of total variation distance, as I said, in the Neyman-Pearson formulation. Just like total variation distance governs the probability of error in Bayesian formulation, at least for uniform prior, this Kullback-Leibler divergence controls the probability of error in the Neyman-Pearson formulation. What we showed last time was that this probability of error can be smaller than 2 to the power minus n dpq. That's what we showed last time. Well, you can divide by n and take a limit. This limit is roughly defined. Okay, if you know some discussion on formal notions of limits, we have to be careful in defining this limit. But I assure you that this limit exists. Okay, and this limit exists, and in fact, what we have shown is that the liminf, if you know what that means, is bounded by this guy. Okay, no problem. But we can just think of this as limit. I don't want to be so pedantic up in this part. So as n goes to infinity, this can be made to, so this goes to 0 very fast, exponentially fast, and the exponent can be made larger than dpq. There's a minus sign here. Therefore, this is an upper bound on beta epsilon p and q. And so this is the following statement. Okay, so this is a very cute handle over the exponent. But is this any good? Is this bound any good? We are happy that this is exponentially falling. It can be made to fall exponentially rapidly, but can we improve over this dpq? And this is the content of Stein's lemma, which says no, you cannot improve. In fact, what it says is for ID distribution, this is exact. The best you can do is dpq. So I haven't shown this. So when I haven't showed the other side of this inequality. A quick remark on some proof: whenever you see an equality like this, you should imagine two inequalities hidden there. This one and this one. Okay, both hold, and therefore equality holds. We have already shown one side of it, and this is the other side of it. In computer science and related areas, these things are called lower bound and upper bound. Okay, an impossibility result will be called a lower bound, and a scheme which achieves something is called an upper bound typically. But as you can see in this example, this notion of lower bound and upper bound can flip based on application. So here it's a scheme which gives a lower bound. So in information theory, we will call these things as achievability and converse results. Okay, so achievability is not a real word, but it's used quite commonly in information theory. So we have shown that a scheme can get you here, and the second part, which we have not shown, we'll show later in the course, says that no other scheme can do better than this. So indeed, this log likelihood ratio test, with threshold being roughly n times dpq. Okay, there was a correction. It was this plus, I think, plus or minus. I don't remember that part. Something like that. Some variance. And there was some epsilon dependence also there, which we had from Chebyshev as 1 by epsilon. Okay, so there was this correct. So this is roughly what we chose the threshold to be. And then it gives you dpq, 2 to the power minus n dpq as the rate at which probability of error can be made to go to 0 for this choice of threshold. And what we are showing here is that nothing can beat this performance. We are claiming, we are not showing it. We'll show it later. Okay, so the largest exponential decay rate of beta epsilon p and qn is dpq, and it's attained by threshold test. So this dpq is a very interesting quantity, this total variation distance. It has similar, this Kullback-Leibler divergence. It has similar interpretation as total variation distance. So what do I mean by that? If dpq is small, the hypothesis p and q are difficult to distinguish. So we can just treat, this is a heuristic statement I just made. So if dpq is small, the hypothesis p and q are difficult to distinguish. Just like we thought when total variation distance is small, hypothesis p and q are difficult to distinguish. Similarly, when Kullback-Leibler divergence is small, this hypothesis are difficult to distinguish. Stein's lemma gives an asymptotic justification of this fact. Okay, Stein's lemma shows us that this is indeed true because asymptotically the probability of error is roughly 2 to the power minus n dpq, n times 2 to the power minus n times Kullback-Leibler divergence. So a small Kullback-Leibler divergence, let's say if Kullback-Leibler divergence is of the order 1 by n, means that you cannot have small probability of error. But later we'll see another justification which will also instantiate this principle for a fixed n. So, but I want you to remember this principle. The difficulty of a binary hypothesis testing problem is related to the distance between p and q. This distance can be measured most formally by total variation distance. But we'll see other versions later where you can also introduce other notions of distances which are not really distances in true sense, like Kullback-Leibler divergence, which we saw now. So if p and q are close in any of these distances, the hypothesis testing problem is hard to solve. It will take more samples to solve it if you're thinking of independent samples. Okay, or it will be harder to solve. Okay, so let's take an example. Let's go back to our example of point toss and try to compute dpq. So total variation, so look at this particular choice of p and q, one where the p is Bernoulli half and q is Bernoulli half plus epsilon. So for this particular case, half plus epsilon by 2. For this particular case, total variation distance is epsilon by 2. Okay. But Kullback-Leibler divergence is half of log 1 by 1 plus epsilon, you can check this, plus half of log 1 minus epsilon. So it's roughly half of log 1 minus epsilon square. In fact, you can replace this log with natural logarithm by an additional factor of ln2. So it's this guy here. So claim now we make is that this ln of 1 minus epsilon square is actually greater than epsilon square. Okay, can you show this? So the easy way to show it is to plot the graph and show it. Okay. So what is this? This is equivalent to showing that log of 1 minus epsilon square, minus sign is here, is less than equal to minus epsilon square. So log 1 minus x, okay, is less than equal to minus x, at least for non-negative x. Okay, x between 0 and 1. So what is log 1 minus x? How do we show this? You can try to plot the functions of you can try to plot these functions and then try to show this. Okay. But this is a very important inequality. I'm not showing it now. I'll give you as a homework exercise to show several such inequalities. Actually, you should be comfortable showing it. So here is something which you should remember. Log 1 plus x is less than equal to x for all x that are greater than minus 1. Okay. So this. Alright, so this is the inequality which we've used here. But epsilon square was roughly total variation distance square. So for this example, this dpq, the total variation distance, the Kullback-Leibler divergence is square of the total variation distance. Okay, and in fact, this kind of relation holds in general. We'll see that later. Before I proceed, I would like to so I kept most of my discussion about discrete distributions, but it's easy to extend all these notions to continuous distributions, in particular those with density. So suppose P and Q have densities f and g, then you can define dpq, the Kullback-Leibler divergence, as the expected value of log of ratio of densities. The theory for discrete and continuous distribution can be very different, but there is a common ground for both the theories. You can, instead of densities and PMF, you can work with ratio of PMFs and ratio of densities. And ratio of densities can always replace ratio of PMF to come up with such a theory. Okay, that's a very high level description of formal probability. So that's what we have done here. So this is log of ratio of density, and it's an expectation, but it can be written as this integral also, because P has density F with respect to this Lebesgue measure. Okay, so this distribution serves the same purpose as for the discrete case. This definition of total Kullback-Leibler divergence serves the same purpose. So you can actually try to see if you can recover some of those results for continuous case using this definition. In fact, this definition of Kullback-Leibler divergence and the discrete distribution version can both be recovered from a more general definition, which perhaps I'll allude to later in the course. Okay. So the log likelihood ratio test G tau can now be replaced with this kind of log likelihood ratio test. So this is for the IID case, where it becomes the log likelihood ratio of Pn and Qn. So if P has density F, its IID copies have densities F to the power n, and this one will have G to the power n. So the log likelihood ratio is just summation log of F by G of xi. So instead of ratio of PMFs, it's ratio of densities evaluated at xi. And we compute this, and so these are sometimes called score functions. So log likelihood ratios, these are called score functions. So we compute the sum of score functions and check if the score exceeds some threshold tau or not. And a good choice of tau is n times dpq, which gives Stein's lemma. Alright. So in this part, I just quickly showed you how this definition of Kullback-Leibler divergence can be extended to distributions with densities like Gaussian distributions, and how even for this extended definition, similar results will hold. Okay, I just alluded to it. I gave you the threshold, the corresponding threshold test to recover Stein's lemma for this distributions with densities. Okay, but for the most part of this, for most of this course, I'll focus on discrete distributions. But I'll give this kind of side remarks here and there so that you can go back and convert all the results to distributions with densities, or maybe even more general distributions based on how much probability you know. All right. But for discrete distribution, you should be able to follow everything in the class. All right. So this is all I want to say in this video. See you in the next video.